This is Knowledge Engineering with Semantic Web Technologies. Welcome to lecture number 4 about OWL, rules and reasoning. Today we will start with semantics for RDF and RDFS. So you remember RDF, which is the resource description framework, which we use to exchange information and encode information within the semantic web. So the question, of course, is why do we need something like a special semantics for RDFS? Because when it was introduced in 1999, it did not provide a formal definition of semantics. It means, okay, of course you need some kind of semantics, otherwise you can't implement that specification, but every definition was given in kind of natural language. And as you know, natural language might be ambiguous. So this, of course, will be difficult then to derive a unique specification from it. So with according consequences. The point was then tool developers for semantic web applications complained about incompatibility. So for example, here triple store developers, they had the very same query at different triple stores with the same RDF data, the same Sparkle query, but it delivered different results. Simply because there was no unique formal specification of the semantics. And the reason for that was, the way it was interpreted, the natural language definition of the semantics was different between these triple stores. So therefore, as a consequence, a definition of a formal semantic really is mandatory. And the semantic web, as you know, requires a shareable, declarative, and computable semantics. And therefore, of course, this is also the reason why we are talking about formal semantics also for the lower level for RDF and RDFS. Simply also because already at that level, we dealt with that previously in the lecture, some kind of reasoning is possible. So reasoning about RDFS facts, of course, would be nice. So here is a simple example. Here semantic web is a lecture, and a lecture is subclass of a course. Therefore, we can also deduce that semantic web is also a course. So, and which statements are logical consequences for the reasoning? This is governed usually by the definition of the formal semantics. So therefore, we need a formal semantics also for RDFS. So what are our requirements? So usually you apply mathematical logics to formalize correct deductions and inferences. So therefore, if we apply a mathematical logic, first we have to talk about a set of statements about which these inferences and deductions can be made. So this is kind of a repetition of things we have already talked about. So you need a set of statements, usually denoted by a capital S in italic. And besides these statements, you also need a relation which defines how valid deductions can be made. And this is the so-called entailment relation, to make inferences about a set of sentences or statements which entails another statement. And these both together, the set of statements as well as the entailment relation, they together form a logic that we need to apply here. So let's define a model theoretic semantics. The basic idea there is we have to find some kind of a mapping for statements of a logic with interpretations. So what we do here is we try to think of RDFS as a logic, and we try to find an interpretation for that which maps this to a kind of set theory, because this is much simpler and we know how to deal with set theoretic axioms and stuff like that. So we define an interpretation. The interpretation usually here consists first of a domain of discourse. This is the capital delta here, delta I, that's the domain of discourse, and this is usually not empty. And for that, you need an interpretation function I. What does this interpretation function do? It's quite simple. First, it maps all atomic concepts to elements of the domain of discourse. And it does the same with the relations. So all relations, properties in RDF and RDFS, they are mapped to relations on the domain of discourse. And then, of course, you have to define a criteria to decide if a given interpretation really satisfies a statement of S. So this is the so-called model relation. The interpretation then if it satisfies a statement like that. So when you have an entailment or something like that, then if the interpretation satisfies a statement, it's a model. So you need that model relation. Okay, let's have a look at the entailment relation. So we know a statement S from our set of statements S is entailed from a set of statements which is a subset of the set of all statements exactly then if all interpretations I satisfying all statements S prime of our set S are also a model for S. So this is of course the formal definition of the entailment relation, which has also to be defined for RDFS. So what we have here then is, you see here a set of statements, and here are two statements, S1, S sub 1, and S sub 2, and they entail another statement S. And I want to do an interpretation of that, so therefore I go here and try to define a model of S sub 1 and a model of S sub 2, and you see here the model of S is exactly in the intersection of the two models of S sub 1 and S sub 2. So what we do here exactly is a visualization of this kind of mapping that we do with the help of an interpretation. And this, of course, again, is here interpreted with the help or visualization of set theory. So you see here, this kind of entailment can be visualized in a rather simple way. Okay, now let's focus on RDFS. So what's happening here? We need a set of statements. Okay, what are statements in RDFS? Yeah, sure. All triples are statements. All triples consisting of subject, property, and object, they are statements, of course. So what's the kind of vocabulary that you use here? So triple can be represented with a vocabulary, which is, sure, the components of a triple can be URIs, blank notes, or literals. So you can write this also in a formal way. You say a triple consists first the subject of URIs and blank notes, then the property is usually an URI, and then the object is a URI, a blank note, or a literal. So from this set, you can make or form statements. But not only single triples are a statement, also statements that belong somehow together in a kind of graph, they also form statements. So this means an RDF graph, which is a finite set of triples, is also a statement. So every RDF graph is a statement. And what you have to define next are interpretation function also for the entailment function to define what does it mean to be a satisfying interpretation for a triple, and then also for the syntax that you use in RDF and RDFS. So also for the RDF syntax, for example, RDF type, or for the RDFS syntax, which is RDFS class, RDFS property, and stuff like that. For these, you need interpretations, mappings to some model theoretic interpretation. So you can do this, and usually one is doing this in step by step. So you start with a so-called simple interpretation, which is an interpretation of general triples. So what is an interpretation that satisfies a given set of triples? And then, of course, you have to take care about the meaning, the semantics of the RDF syntax, the RDF commands. And then on top of that, you also have to take care about the meaning, the semantics of the RDFS commands. Simply because you have seen with RDFS, you are able to draw and to infer new knowledge with the help of these entailment relations that you can do, for example. So these, for example, class hierarchies, there you can deduce or infer new knowledge, new triples. But how to do that in detail, of course, is not part of the course. So if you are interested in the details here, I can give you some hints and a detailed explanation of that in the extra parts of that lecture at the end of the lecture, which is not part then of the grading of this course. In this course, this should be sufficient as an idea why you need a semantics, a formal semantics for RDFS, why is this useful. And of course, we want to continue with our languages for the semantic web. We have already learned about description logics, which is used to define ontologies and knowledge bases. And of course, we want to take a look at the semantic web language for these ontologies, which is the so-called web ontology language with which we start in the next part of that course.